watching.
Now we're going to talk about the ability to take the first and second derivatives and use them to find out pretty much everything that's going on in a function. And we call this curve sketching, the ability to create a graph using calculus of any function. And functions are critical to our lives. So many applications in so many fields require the use of some mathematical tools to analyze and build functions. Here are some general guidelines for analyzing the graph of any function. You need to look at the function and determine what its domain, remember domain is the input values, the values that can go in, and what its range is. Secondly, you're going to need to determine the intercepts. Where does it hit the vertical and horizontal axis? You're going to need to use calculus and some pre-calculus to determine where the asymptotes lay. They're where the function may not be able to ever reach a vertical or horizontal value, a value of input or output. And finally, look for any kind of symmetry. Is the function even or odd? Does it have any other kind of symmetry about certain axes or lines that we need to know? Once you've done that, you're going to use calculus to look for minimums and maxima, extreme values. These are local minima and maxima, or sometimes they're absolute minima or maxima. You can also use the second derivative test to look for points of inflection and concavity in the function. Is the function concave up or down? And of course, all of these things, the extrema, points of inflection, occur where the derivative, whether it's the first or the second derivative, is equal to 0, or in some cases does not exist. And you're going to use those to find those relative extrema, minima or maxima, and points of inflection, because points of inflection are the boundary points, you remember, between concave up and concave down. But when you've done all these things, it's very easy then to sketch and understand what the function is doing. Now let's look at a couple of examples. And I've put the guidelines over here to remind you of kind of this general process of looking at a function and then being able to analyze it. Now I've graphed this for you so you can kind of see how we uncover the features of the graph from using this process. So first up, what's its domain and range? Well, domain is what goes into the function. And what we're looking for in domain is, are there values that cannot occur for the input? And radicals and denominators, those are the kind of things that will limit input. Another thing that limits input is real-world kind of functions. For example, negative time, that could limit or restrict your domain. Well, looking at this, I see x times the square root of 9 minus x. Well, the first part, the x, is not going to be restricted, but certainly radicals, we know, have to incur positive values, especially when we're taking even roots like the square root. So the square root of 9 minus x can never have an input that's below 0. Therefore, 9 minus x must be greater than 0. So x must be less than or equal to 9, or else this domain will cause a problem and cause a negative in the radical. So the only values for input that are going to work are x values less than or equal to 9. Now, as far as the range goes, we're going to find out the maximum using calculus, but it looks like f of x is only going to be restricted by the input values that are going in. So the fact that x has to be less than or equal to 9 is certainly going to limit the range. We don't need to specifically figure out what that is yet. So next we're going to look at the intercepts, asymptotes, and symmetry of this function. And of course you can see them here, but we're assuming you can't. I'm just using this to help build what the function looks like. But intercepts occur where the values for the input or the output are equal to 0. For the x-intercept, that occurs where f of x equals 0. For the y-intercept, you're going to set x equal to 0. For the x-intercept, you're going to set f of x equal to 0. So let's do the second part first. Let's do the y-intercept since it's a little bit easier here. The y-intercept occurs where x equals 0. That is within the domain of this function. So if we put in a 0 for x, f of 0 is equal to 0 times 3. If we put in a 0 for x, and we get 0. So there is a y-intercept at 0. So to find the x-intercepts, we're going to set f of x equal to 0. And when we do that, using the zero product property, either this first part, x, could be 0, or this second part under the radical could equal to 0. So either x is equal to 0, that's one solution to this, or the square root of 9 minus x equals 0. which if you square both sides and then add x to both sides, you're going to get that x equals 9 sets this equal to 0. So there are two x-intercepts here. One is at x equals 0, and the other one is x equals 9. So intercepts, we have x-intercept at 0 and 9, and a y-intercept at 0. So when we are looking at asymptotes, for horizontal asymptotes, we're looking at, as x approaches positive or negative infinity, is there some sort of a limit? So we have to use our rules to evaluate that. And then for vertical asymptotes, we're asking the question, for what values of x does the limit of the function not exist? Is it approaching positive or negative infinity as x approaches some certain value? That's going to tell us we have a vertical asymptote. Well, with polynomial functions like this, even ones with radicals, you can use direct substitution to figure out both of these limits, and we're not going to have asymptotes for these. This is true of all polynomial functions that do not involve denominators, and this is certainly one of those cases. So looking at a horizontal asymptote for this function, there is no value of x at positive infinity that can go in here because positive infinity is not in the domain. However, negative infinity is, and if we put negative infinity into this function for x, we're going to get an infinite value. So there is no horizontal asymptote. As x approaches negative infinity, this function continues to get smaller and smaller. Now, vertical asymptote, there is nothing that is going to cause this function to have a limit that doesn't exist, at least within its domain. If we were to evaluate this function and look at its limits all throughout, the limit at all the x values does exist. It's a continuous function. There are no breaks, at least within the domain. So as for asymptotes, we have neither horizontal or vertical asymptotes in this polynomial function. Additionally, there's not going to be any symmetry here as well. And you would look to see whether the function was some sort of an odd or even function for symmetry, and that's not the case here. So let's look at the first derivative now. I'm going to rewrite the function in exponential power form so that I can use my derivative rules on it, and you're going to have to use the product rule coupled with the chain rule to do this. When you do that, when you take the first derivative, you're going to get, when you take the derivative of the first part times that second part, and then we're going to take, since it's the second term, the derivative of the second part, and also multiply it by the first part. Using the chain rule, you know the derivative of that 9 minus x to the 1/2 power is going to be 1/2 times 9 minus x to the minus 1/2 power, and don't forget to take the derivative of what's inside minus 1. So if you had trouble with that, you probably need to go back and review your product rule, but that's the derivative, the first derivative of the function. So after we get this put in a nice form that we can algebraically manipulate it, we're going to add that negative term to both sides, getting the square root of 9 minus x equals x over 2 times the square root of 9 minus x. And although that looks nasty, we can multiply both sides by that denominator to get rid of the denominator, and the radicals wind up canceling each other out, and you get 2 times 9 minus x equals x. If we distribute that 2, we get 18 minus 2x equals x. Add the 2x to both sides, you're going to get 18 equals 3x. So therefore, x equals 6 winds up being an extrema on this function. So I'm going to make a table of values. Second derivative's really going to be a time-consuming business here, and it's not going to tell us much. So we're not going to fool with the second derivative other than to look at its overall concavity. So let's make a table and evaluate this. I know the extrema occurs at x equals 6, so I'm going to use x equals 6 as the center point of this analysis of this table. I'm going to look at x equals 0 and x equals 8 because they're easy to plug in here and find the values for. At x equals 0, the function is 0. At x equals 6, put in a 6, the function is 10.4. We're going to find out whether it's a maximum or a minimum, but it looks like a maximum just from this. At x equals 8, 8 times the square root of 1 is 8. Now let's look at the first derivative test. If we put in a value of 0 into this first derivative, we get a positive minus 0, so it's a positive. If we put in 6, we know we're going to get 0 because this and this will cancel each other out. And if we put in 8, we're going to get a positive number minus a bigger number. We're going to get a negative number here. So what that tells us is Tells us the function is increasing, then it's flat, then it's decreasing. And the second derivative, if we were to find it, is going to tell us that it's concave down throughout, because we're going to get a negative number when we put in the second derivative. So you've probably been following all along, but let's look at the function itself and see if it meets everything that we've done. Its domain, all x values less than 9, or equal to 9. Its range values are only restricted by those, and it winds up being from negative infinity to positive 10.4. Its intercepts for the x-intercept occur at 0 and 9. Its y-intercept occurs at 0, and that's the only y-intercept. Its asymptotes don't exist. There are no asymptotes because there is no horizontal limit, there is no vertical limit for the function. There is no symmetry, but it does have an extrema at x equals 6, where it has a maximum because it increases and then decreases before that point. Also, the function is concave down throughout. Let's try this process on the graph of f of x equals x plus 2 divided by x minus 2. Looking at the domain of this graph, what are the input values? Well, things that cause input to not be possible are things like the denominator being equal to 0. So if x equals 2, this thing is going to not exist. So the domain is going to be all real numbers with the exception of x equals 2. We'll hold off on the range, but it looks like the range is going to be just about anything that's possible based on those input values. There may be some horizontal asymptote we find, and we can always modify that. The x-intercept is going to occur where f of x equals 0. So if we set f of x equal to 0, we get 0 equals x plus 2 over x minus 2. In a rational function, that's only going to occur where the numerator equals 0. So where x plus 2 equals 0, that means x is going to be equal to negative. Therefore, x-intercept occurs at x equals negative 2. We get the y-intercept where we set x equal to 0, so f of 0 is equal to 0 plus 2 over 0 minus 2, that's equal to negative 1. And notice I've plotted both the x-intercept and the y-intercept on this graph. Now let's look at the asymptotes. So for the horizontal asymptote, we have to look at what's the limit as x approaches positive or negative infinity of the function. If you remember your rules for limits as x approaches infinity for rational functions, when there's a rational function, we're going to look at those leading terms, leading power terms. And in both the numerator and the denominator, x is to the first power. Therefore, it's going to be the ratio of the leading coefficients, which is 1 over 1. So we are going to have a horizontal asymptote at y equals 1, which I'm now going to draw. So the function will never equal y equals 1. And the same thing happens at negative infinity. If we put in a negative infinity, the same value occurs. Therefore, I need to modify my range to include all real numbers for y except y equals 1. Now for the vertical asymptotes, we look for what x values cause the function to not exist. In other words, for what values of x is the limit as x approaches that value of the function not exist? Is it going to positive or negative infinity? In a rational function, that occurs where the denominator equals 0. Because if we put in a 2 and try to evaluate the limit as x approaches 2 of this function, we would get values of positive or negative infinity as the case may be. Therefore, the function has a horizontal limit at y equals 1 and a vertical limit at x equals 2. It causes the function to not exist. So I've now drawn the horizontal and vertical asymptotes of this function. Is there symmetry? I'm going to say that there is likely symmetry about the asymptotes that we've just drawn. Now on to extrema, where does the derivative equal 0? So the derivative is going to be found using the quotient rule. The low d high minus high d low over the square of what's below. If you need help with that, you need to go back and review the quotient rule. And when we simplify it instead of d equal to 0, we get 0 equals negative 4 over x minus 2, the quantity squared. Well, in fact, that's never actually going to be equal to 0. There are no values of x where the slope is going to be exactly equal to 0. However, there is a critical number where the derivative is going to fail to exist, and that's at x equals 2. So therefore, where the derivative is not going to equal 0. So we don't have any extrema, but we do have a critical number at x equals 2. So let's talk about points of inflection. We're going to take that simplified first derivative, and then we're going to find its derivative to find the second derivative. And I'm going to rewrite this, rather than using the quotient rule on this, I'm going to rewrite it in terms of exponential powers. It becomes -4 times x minus 2 to the -2 power, which I can use the power rule and the chain rule to find the derivative of pretty quickly. And when I do take that derivative, I get -4 times derivative of that x minus 2 term, which is -2 times x minus 2 to the -3 power, times the derivative of what's inside 1, that's the chain rule. And simplified, that becomes +8 over x minus 2 to the 3rd power. Well, it's never going to be equal to 0. That numerator is always going to be 8. The denominator, even if it gets gigantic, this number never actually equals 0. The one place we need to be concerned about, which is going to be a point of inflection, is at x equals 2, because the second derivative will fail to exist at x equals 2. So interesting thing about this function, you don't have extrema, but you do have critical numbers at x equals 2, and that critical number is a point of inflection where the function is going to change from concave up or down to another concavity, the opposite of the up or down. So let's make a table of values and plot some points here. So we're going to pick 2 because it's our critical number, x equals 2, and we're going to pick points on either side. Let's do 1 and 3. I picked 1 and 3 because we already know the value at x equals 0. We already know a value at x equals 2. So let's pick some new points. At x equals 1, the function is -3. At x equals 2, we know the function does not exist. And at x equals 3, the function equals 5. In all three cases, we're putting it into f of x. Now let's look at the patterns of the first derivative. Interestingly enough, this function is always decreasing. If we look at x equals 1 on the left side of the critical number, we get -4 over a positive number because the denominator is already always squared. If we look at x equals 3, we get a -4 again over a positive number. So always, except at the critical number, the derivative is negative. The slope is negative. This function is always decreasing. Then when we plug in the values of x into the second derivative, we see that on the left side of 2, we get a negative number, meaning that it's concave down on the left side of x equals 2. And then if we put in values like 3, we get a positive over a positive, so it's concave up to the right of x equals 2. So we now actually know a lot about this function. Let's kind of go to the big graph here, and I can tell from the derivative test that it's decreasing throughout, it's concave down over here, and it's concave up over here. Let's plot some more points and see. So if we plot these 2 extra points, we start to see some patterns emerging when we put it all together. Here's that downward concavity. So on this left-hand part of the graph, on the left side of the asymptote, I've kind of sketched this in. I think it looked something like this. Concave down, always decreasing, going through these 3 points. Right-hand side of the graph, it's doing the same kind of thing. It's always decreasing, it's concave up, and I only have 1 point, so I'm going to use some symmetry here, though, because clearly there's symmetry about this axis right here. So I'm going to plot a couple of points and see if that holds true. And sure enough, if I plot 2 more points, I see the beautiful symmetry of this graph. And I can see it's going to be going through these points and have all the properties that calculus and pre-calculus tells it is going to have. So that's what you need to know about curve sketching and understanding of functions using both your pre-calculus and calculus tools to get a good picture of what's happening with a function.